The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker will be talking on one of those E701 documents is on cementitious materials for a new age. Our speaker is Darrell Elliot. Darrell is the Technical Services Manager for Buzzi, Unicem, USA, and is a fellow of the American Concrete Institute. Please help me welcome Darrell.
Okay. Of the four documents, one is our cementitious materials, and we're going to go through some of what we cover in this document. As Dave mentioned earlier, we are intentionally not overly technical in these documents. It's meant to be something where you can get some general information and understanding of the materials without getting into the heavy-duty chemistry and process science and all of that sort of stuff that we do cover in the technical committee documents. Cementitious materials are covered in 225 for Portland cement and other cements, along with 232 for fly ash, 233 for slag, 234 for silica fume. So we're drawing this one 30-page document is covering the material from 4 other technical committees and their documents. And we start with our basic concrete making materials. We're making a cast-in-place stone by gluing back together pieces of rock and sand with a paste made up of a cement and water. And that's how we've done it for the ages. Now, of course, things have changed a little bit, and there's a lot of different powders that we can use these days. And those powders are now, instead of just referring to everything as cement, we're calling these all cementitious materials. And it covers the range of our Portland cements, the blended and specialty cements, the slags, and then the pozzolans such as fly ash, and clays, and silica fumes. All of these materials are the result of some pyroprocessing. They're all processed in flames. And we cover in the document, we give you a brief overview of how Portland cement is manufactured. I'm not going to go into a whole lot of the detail other than just to show how it's laid out. We start with some quarrying of, can anybody see that? I can't see. Oh well, so much for the pointer. We start with quarrying our stone. The major component is lime. We take that from limestone as the most popular source of lime. And then there's several other ingredients that we're using for the other materials. There'll be sands, clays, and a lot of recycled materials too, post-industrial materials, mill scale, slags, fly ash, and other such substances that we can use to get the chemistry we need. We're also burning an awful lot of waste materials at a lot of the plants. So where we've been considered one of the targets for the environmentalists on our for what we do in CO2 emissions, we're doing an awful lot to use recycled materials. A lot of our plants are burning waste chemicals as fuels. A lot of our plants are burning used tires as fuels. So we crush all those materials together. Then the various raw materials on the left are stored in silos, the sources of the lime and the silica and the iron. Then we crush all of that down to a powder. It's blended, and then it goes into the kiln. The kiln is the inclined tubular assembly you see in the middle of the picture. It's set on an incline. We're running flames through there. We're heating that stuff up to about 1,800 degrees Celsius or 2,700 Fahrenheit. And at that point, all of these compounds that we've mixed together are going to break down to their elemental state, and then recombine based on the total combination of those materials that we have in there. So it's a giant chemical equation that we're solving, and when we're running a cement kiln, we have to account for every component and every ingredient. For example, when we started burning tires as a fuel, a lot of tires are steel belted. Well, the carbon black, the tire rubber, burns very efficiently and it all goes away. But the iron left over from the steel belts stays in the kiln with the material. Now, iron is a normal component of cement, somewhere in the range of 3%. So when we burn tires as fuel, we have to account for the amount of iron that's going to be in those steel belts to keep that same 3% going. So it's a constant balancing act of all of that chemistry. And then once that material has been burned, it forms over into what's called clinker. And this is a granular material, something around the size of marbles that's going to come out of the kiln. We'll rapidly cool that with air. And then later that is ground in a ball mill to a powder in conjunction with some gypsum. The gypsum is added to give us our control of the setting of properties of the Portland cement. And we end up with a granular material that's going to be average somewhere around 25 microns in size. There's 5 major types of cement. The Portland cement, ASTM C150, the type 1 for general purpose, 2 for sulfate resistance, 3 for high early, 4 for low heat, and 5 for the high sulfate resistance. There's also a group, there's another 3 where these same types are combined with an air entraining material so they can be sold as an air entraining cement. This was the common way of making freeze-thaw concrete, was using air entrained cement. Nowadays that's much more often taken care of by chemical admixtures, and there's very little of the air entraining cement made, but it is still made. The other cements we deal with are, as I said, the air entrained materials, the blended cements, and while they're very close to where we are with the Portland, I'm going to reserve this discussion of the blended to the cements to the end. It's going to make a little more sense in the process. White cement is another common construction cement. It's a little different. There's less iron, more aluminum in it, but it's not under C150. And then there's some other special materials that we cover in the document. They're used in different applications. Have more differences to the Portland. That's our masonry and mortar cement. The rapid setting cements, the calcium aluminates. There's expansives, cements, plastic cements, water repellent cements, and then the oil well cements. So these are all covered. We give a few paragraphs to each of these, just kind of give you a little background of what they are and how they relate to the rest of it. And we go into the supplementary cement materials. The closest one to cement is slag cement, ground granulated blast furnace slag. Now this is a glassy material that we get from burning iron ore with limestone flux and coal. They extract the iron, and what's left over is a calcium silicate material. Very similar in makeup to cement. It does have hydraulic cement properties of its own, and it does have some pozzolanic activities governed by ASTM C989. And very similar to the process we go through with the manufacture of Portland cement. And the biggest difference is that instead of a long horizontal revolving kiln of fire, we have a static vertical blast furnace of fire. Same process where we're breaking down the material, we're crushing limestone. Limestone is used as a flux in the melting and the reduction of the iron ore. It's going to be iron ore, limestone, and coal. That's going to be put into the blast furnace, broken down, and we tap the blast furnace. The blast furnace would actually be in the background of that picture. And this is actually daylight when I shot these pictures. That give you an idea how bright the flame is inside of there. It stopped the camera down to it looks like it's that dark. This is like being in the bowels of a volcano when you walk inside one of these plants. And you can see where the fire going through the floor, there's trenches, and they'll open the ports of the blast furnace and let that molten iron run out. That's at the bottom. It's the most dense material. They'll let it run out, and they can tell from the appearance of the liquid flow when it's starting to get some of the slag in combination with it. At that point, they'll dam off that trench, and you see the little white bags. That's a vitreous clay compound that they can drop in that hot molten flow, and it immediately hardens to serve as a little dam in each of those trenches. The iron, the pure iron, will run down one trench. Then they'll open it, let it run down the other trench for a while, where it's a transitional material of iron and slag. Then when it gets to be pure slag, they'll dam off that trench and then open the third trench where they're running off just the pure slag. The pure slag then goes into a granulator. The hot liquid coming in from the top right corner is what we call the liquid runner. That's the hot feed, the liquid slag, liquid rock, white hot, flows like water. And what you see down below, it's hard to make out to do any better in this picture, but this is all I had to work with. What's down here is spray openings of water. And we're spraying water underneath and through this stream of, again, 2,700 degree material. That material is then frozen, if you will. It's vitrified, it forms a glassy material, and then it's in granules, and that's what we use to take then to the cement plants, where we grind it up in a ball mill. In fact, we use the exact same ball mills that we've used for Portland cement to grind a powder, again, similar to Portland cement. The next in the sequence is our fly ashes. The fly ashes can be a Class C or a Class F. This is the finely divided residue that results from the burning and combustion of pulverized coal at a power plant. We're going to get spherical particles. And what used to run up the smokestacks, of course, with all the interest in environmental approaches, we can't let that happen anymore. We're catching that material. That's the fly ash we're putting in concrete and clean stacks. The coal and air goes into the flame. We get the power plant, they're really just looking for the BTUs. They're not looking for a product. They're looking for the BTUs out of the coal. And then that exhaust, which contains the fly ash, is passed through, the air is passed through these electric precipitators, and the fly ash will drop out of the discharge into these hoppers, and then that material is carried on through a broker and silos and delivered to be used in concrete. It's a spherical particle. We're using it as it comes out of the flue. We're not processing the fly ash typically. The particles are spherical. They can be solid spheres, hollow spheres. We see some hollow spheres with smaller spheres inside of them, and we see some of the broken up spheres. And this material is divided by ASTM C618 between a Class C ash and a Class F ash. And Class C ash is different in that it has a higher carbon content, and that a higher calcium content or lime content. And it's usually going to be lighter in color because the C ash is usually burn cleaner, and we usually have less carbon and iron in that ash when we take it from the power plants. It has pozzolanic and some minor cementitious properties of its own. The Class F ash, on the other hand, is going to be a lower calcium oxide or lime content, will be darker in color, the reverse. It's got more of that carbon, unburnt carbon left in it, and it'll have more iron in it. And this comes from the anthracite and bituminous coals as opposed to the subbituminous and lignite coals that give us the C ash. And the various types of coals are located around the country. So where the coal comes from is going to determine what class of ash you have available. Typically, what's in the eastern third of the country will be the Class F ashes. Typically, more what's in the western two-thirds of the country will be the C ashes. Now, that raw fly ash will have a variety of sizes. The sizes can run from 2-3 micron size on up to 60 micron sizes. With that material, we know from back at our basic high school chemistry classes, more surface area, more reactivity. So what some of the fly ash folks have done is they've figured out that they can take those real fine particles out of the bulk fly ash. They'll run it through a particle separator that'll separate those finer particles from the coarser particles, and they will sell just the fine particles as an ultra-fine fly ash. And because it's all the smaller particles with that higher surface area, it's a much more reactive fly ash than the traditional unsorted fly ash. The next one under C618 for pozzolans is our natural pozzolans. And the one that we see the most of is Metakaolin. And this is from the kaolin clay, mined, washed, calcined, and then put out in a fine powder. And it again gives us some pozzolanic reaction with some additional hydration. And the last in the sequence is silica fume. And silica fume, again, is coming out of a fire. It's the residue that results from the production of silicon and ferrosilicon metal, where the ores are placed in these kettles with an electric arc, electric probes that are put in that cause an arc across it, causes it to break down. And the smoke that rises up is the fume, that is silica fume. And again, this material used to just go up the stacks. Now we're collecting it. We're using that material. That is going into our concrete. It is a very, very small particle compared to the others. Silica fume is some 150 times finer than Portland cement. Because it's so fine and has a very low bulk density, it's very difficult to handle. So what the folks that sell this material do is they do two processes. One is a dry compacted silica fume, where they blow the silica fume through an electrostatic charge and causes the material to clump together just from static. If you handle this material, it's going to feel like a coarse sand. But if you rub it just a little bit, those what feels like sand grains will break down into that very fine powder. Or it can be suspended in a water slurry, which again will let us get a whole lot more material in a lot less space than we would with just a raw silica fume. Now, the supplementary cement materials that we're using, why are we using them? Well, it started with, this is something that can reduce our materials cost. We found this was a replacement for Portland cement. Fly ashes, back when they were introduced into concrete, were typically a fourth to a third of the cost of Portland cement, and we could use that and get some comparable strengths and performance out of it. That was the origination of the process. Well, as we used more and more of these materials, we found not only were we saving some money, and this is kind of counterintuitive, we're getting a waste product that's cheaper, but we're actually making better concrete with it. We found that not only could we get some economy by using these recycled materials, we find that they also contribute to improved strength and improved durability properties, lower permeability, reduced heat of hydration. So now we've got a performance advantage. We're actually seeing that in most high-performance applications, we're tending to want these waste products in our concrete. Where before, in the beginning, you had to kind of beg an engineer or an owner to let you put this material in their concrete. As we became to the position of understanding more the strength and performance properties we were getting from these products, that this is something we want to include in our concrete. And this is something that you will almost always see in those high-performance applications, high-strength, high-durability applications. And then the third impetus for the use of these materials is the environmental, the sustainability angle. We're utilizing materials that would otherwise be landfilled. We're reducing carbon dioxide production and energy consumption when we use these materials as a partial replacement for Portland. The energy that's embodied in those materials, in these supplementary cement materials, is already expended in the primary process that they were derived from. So for every ton of supplementary cement material, we're saving a ton of Portland, we're saving a ton of CO2 emissions, we're saving an awful lot of energy consumption by using these materials. So what do they do for us in our concrete? Why are they so good in our concrete? Well, first, let's just talk about simple particle packing, particle size distribution. I've got the Blaine sizes, and Blaine doesn't always make sense to a lot of people. You'll see these listed on mill reports in either the 3-digit or the 4-digit formats. The numbers mean the same thing. It's either square centimeters per kilogram and square meters.
Square centimeters per gram or square meters per kilogram.
Okay, and thanks to metric, everything's just factors of 10. So it's just a factor of 10 in the moving of the decimal one place or the other. So if you see a blane that says, I've got my cement is a 376, that's the same as seeing a cement that has a blane of 3760. It'll just be in whether it's going to be in the lower units or the higher units. But I've also given you the particle size of that, just so we can relate to an absolute measurement. Portland's going to average somewhere around 25 microns. Slags are going to average somewhere around 12 microns. Both of those are processed in ground, so there's various sizes. There's a limited range of sizes. Fly ash, since it's not further processed, has that much larger range of sizes, can be anywhere from 3, 5 on up to 60 microns. And the ultrafine fly ashes are usually going to be classified to be just those smaller particles. And then we have silica fume, which is down at 0.3 microns. Very, very small relative to the others. I didn't have, what's our particle size on Metakaolin, Dave? Don't know it offhand. They did more of that than I ever did. So. What happens in our particle distribution, just like we want gradations of our aggregates to be distributed over a range of sizes, we also can take advantage of particle packing with our cement materials. And if you look at any of the programs that are used in designing the new self-consolidating concrete mixes, they will not only do a combined gradation of the aggregates, they will do a combined gradation of the entire mix that'll take you all the way from the coarse aggregate, through the fine aggregate, through the cementitious materials, and even include the air entrainment. And look at that distribution of those particles throughout that size to get the mixes that'll behave properly, that'll give you the flow and the cohesion that you need. And when we use the cement materials, the other cement materials of the other sizes, we can take, instead of on the left where we have the 5 cement grains fit in that one space with some gaps in between them, we can pack little pieces of fly ash, slag, silica, fume in between those cement grains. And now when these cement grains are trying to spread out their fingers where they'll reach and connect into the next grains, they've got to span a larger space when it's just cement grains, so they have to span a much smaller space when we have those smaller materials stacked in between. The other side is the chemical side. And this is what's going to be on the test after. Y'all are going to have to fill in all the blanks for this table. I've arranged them in order where I've got the higher calcium to the left, lower calcium to the right, and conversely, lower silica to the left and higher silica to the right. And you can see on each of the materials, we have lots of the same chemistry in all of these materials, and we run from a 65% calcium content on down to 40s, 24, 9, nothing. Silica contents from 22 on up to 38, 40, 55, 98. So the materials complement one another, and our cement, because it's at that 65-22 ratio, we've got more calcium than we have enough silica to hydrate completely. So we end up with, in the hydration, cement and water joins in hydration and forms calcium silicate hydrate, and there's leftover lime. There's leftover calcium that doesn't get used. That's free lime. That's something that's can be dissolved out and leach out of our concrete, can lead to permeability and durability problems later. If we look under a microscope, we would see that these grains would be close together, growing out those little projections, trying to crystallize, and we'd have gaps in between there where that free lime and water would be. By using a pozzolan, and what a pozzolan is a silicious, aluminosilicous material that when put in the presence of water and calcium hydroxide, or free lime, will react and give us more calcium silicate hydrate. So these materials consume that weak, leachable free lime and replace it with more cement matrix. And gives us a much more dense mix. This is measured in our permeability, surface resistivity testing. Just about any time you're trying to do low permeability, you're going to want to put one of the pozzolans in there to reduce that permeability, and that's what gives us our big advantages on strength and our big advantages on the durability issues. Now, I try to do analogies of things that make sense to me, so I'll break down the stages of hydration. I put it kind of in rocket stages. The C3A compound, that's like our ignition. That's what gives us our first liftoff. When the water gets with that C3A, it makes heat. And that stuff wants to harden very quick. In fact, we have to use gypsum to hold it back, or the cement would take off far too fast for us to use properly in the field. That's what's just getting us off. Then the first stage, the C3S, is the next most reactive component, and that's going to attribute our strengths from that 1 to 7 and maybe 14 days of hydration. Then the next stage, the C3S kind of runs its course, then levels out. Then the next stage, the C2S, kicks in. And the C2S is going to pick up where that leaves off, and that's going to get us out to that 28-day mark. And magically, we run 28-day strengths on concrete because Portland cements pretty much run its course in about 28 days. You will see some minor strength improvements beyond that date, but not very much. Then we have, if we have slag in the mix, then that's reacting, and that's going to carry us in and give us additional strengths from 21, 28 on up to 56 days. And then the last thing that happens is our Pozzolanic reaction, where those aluminosilicates are reacting with our free lime and giving us even more calcium silicate hydrate that carries us on out further. And then, regardless of which combinations of these powders we're talking about, the fineness is like our throttle. We can take any of these materials, we make them finer, they're going to go faster. We make them coarser, they're going to go slower. That kind of breaks down just the basics of what we expect to happen and how that sequences out. Now, back up, in the document we talk about Portland, then blended, then the supplementaries. But the blended materials are Portland and the supplementals. So we've got to kind of understand what the supplementals do before we talk about the Portland. The blended cements with whichever of the supplementals, you're going to get the same kind of performance that you would get if you use the two ingredients separately. Now, under C595, we used to have 5 types, and it was broken down, it was bracketed by proportions of the pozzolan in Portland modified and Portland pozzolan. Then slag was broken down in 3 brackets of the quantity of slag in those. We have since eliminated 3 of those, and we've just gone to Portland pozzolan cement and Portland blast furnace slag cement. So we eliminated the bracketing of the less than 15 and the 15 to 40, and now it's just type 1P, which is pozzolans up to 40%. And we now put in parentheses behind the 1P the percentage of pozzolan used. Same thing with slag. The 3 brackets are eliminated. Now it's just 1S with parentheses stating what percentage of slag is in the mix, up to 70%. And there are 2 new ones. There's Portland limestone cement and Portland and the ternary blended cement. Portland limestone, type 1L, can have from 5 to 15% limestone. And again, the percentage of limestone would be in parentheses behind the 1L. And type 1T, the ternary blends, we can have 2 other materials put with the Portland. It can be any 2 of limestone, class C ash, class F ash, slag, silica, fume, any of these can be put in there, and our limits here are we cannot have more than 15% limestone, we can't have more than 40% pozzolan, and we can't have more than 70% total of the supplementary cementitious material stuck in that blend. And that gives us the rundown of where all our cements are, and I think I got it in under time.
All right, thank you, Darrell.